Okay, so on this example, you see that you have the graph of x squared over 1 minus x squared, and you see also the first and second derivatives given over on the side. Those derivatives are going to be used in parts D, E, and F, as you see there. We're going to jump in, though, right at the top with the first part. So to determine the domain of the function, you are looking for what values make this undefined, and clearly the denominator of the function for the domain, the denominator cannot equal 0. So you would set that denominator equal to 0 to find out what those values would be. So that would mean you have x squared equals 1. So by taking the square root, you clearly get plus or minus 1 as two values that are not allowed in this function. So your domain would be x values such that x cannot equal plus or minus 1. X is a subset of real numbers. So we've defined the domain of the function. We can move on to the intercepts now. So for part B with the intercepts, the first one I will look at is calculating a y-intercept. To get the y-intercept, you set x equal to 0. So in your original function, setting x equal to 0, you would have 0 over 1 minus 0 squared as your function. We were squaring the top, but it doesn't matter because it's 0. And so your answer is 0. So 0, 0 is your y-intercept. To find your x-intercept, you set y equal to 0 and solve. And so you will get, setting y equal to 0, you cross multiply. You still get 0 equals x squared. So you get the exact same point that you did for the y-intercept, but that tracks because it's the origin. And so your x-intercept is also the point 0, 0, but there were no other points as well. So now we found our x and our y-intercepts. So domain is done. Intercepts are done. We will now go in and look at the asymptotes. So first things first, in the asymptotes we'll find the vertical asymptote is where we'll start. So in that vertical asymptote, we return to those points that made the denominator 0. Those are the points that where the vertical asymptotes will occur. So you have a vertical asymptote at positive 1, and you have another vertical asymptote at negative 1. So what you have to do is then test, right, if we were just very quickly sketching, at positive 1 and at negative 1, you have asymptotes. What you need to do is test just to the left and just to the right of each of those asymptotes to find out if it's trending off to positive infinity or negative infinity. So we write 4 different tests here. We will do the limit of the function as x approaches negative 1 from the negative side. We will do the limit of the function as x approaches negative 1 from the positive side. We will do the limit of the function as x approaches positive 1 from the negative side. And the limit of the function, lastly, as x approaches positive 1 from the positive side. So effectively what you're doing in each case is you're just testing a number slightly to the left and slightly to the right of each point. So for negative 1, you're choosing a number like negative 1.1, and on the other side you might choose negative 0.9. And over here you'll use a number like positive 0.9 and positive 1.1. And so you can evaluate, you really just want to know, if you plug those numbers in, is the number positive, meaning is it going up to positive infinity, or is it negative, meaning it's going down to negative infinity? We don't need the number, we just need to know if it's positive or negative. Okay, so remembering that the function is x squared over 1 minus x squared, then we're plugging in a negative 1.1, for example, into here. So you're going to get a negative 1.1 squared over 1 minus negative 1.1 squared. Well, the top is clearly positive because it's squared. And the bottom, you're having 1 subtract negative 1.1 squared is bigger than 1. 1 minus a number bigger than 1 means it's negative. So that means on this side, the answer is approaching negative infinity. From the positive side, you put in a number like negative 0.9 as a test. So negative 0.9 squared, 1 minus negative 0.9 squared. The top is a positive again because you're squaring it. This time, negative 0.9 squared is slightly less than 1. 1 subtract that number is a positive. So this side, the limit tends to positive infinity. Okay, so we knew on one side it was negative infinity. The other side it's positive infinity. That line's no longer there. Plugging in a number just to the left of 0.1 is a number like 0.9. So putting in a positive 0.9 squared here, 1 minus 0.9 squared, the exact same answers as the line above, because the x's have been squared. So for the same reasoning, you get positives, so that number goes to positive infinity. And then plugging in 1.1, you're going to get the same answer as the very first line that I wrote. You're going to get the same answer here as you do there, because the negatives would become squared. It's an even function. So here you get a positive on top, a negative on bottom, and that goes to negative infinity. So we knew it was positive infinity on this side, negative infinity down there. All of that is the work that's done for the vertical asymptote. We also have to work out the horizontal asymptote. So for the horizontal asymptote, we do a different test, and there's a few different ways to do this. I'm going to do this by employing L'Hopital's rule and looking at the limit as the function approaches infinity. So if I do the limit as x approaches infinity for the function, which is x squared over 1 minus x squared, to work out infinite limits, what we're going to do is divide everything by the highest power of x. That's a trick we can try. So limit as x approaches infinity. If you divided everything by x squared, and x squared over x squared, if you divide everything by x squared and then cancel some stuff, you have limit x approaches infinity of 1 over 1 over x squared, subtract 1. Well, the limit of any fraction as x goes to infinity is 0. The limit of 1 is 1. The limit of the fraction is 0, and the limit of 1 is 1. So here you get an answer of negative 1 for your horizontal asymptote. So, or for the limit. So that means the horizontal asymptote is at y equals negative 1. So again, if you were thinking of your graph at negative 1, you would have a horizontal asymptote. And for this question we want to know, we have to do two tests now. You check way over here at positive infinity or so, like a number like 100, and you just test, am I above this line or am I below this line? And you test way over here at negative 100, and we're going to test, am I above the asymptote or below the asymptote? So we quickly do a test. We plug in negative 100 into our equation, and so you'd have negative 100 squared over 1 minus negative 100 squared. And here you get negative 9999. That is a number that is slightly bigger than the negative 1. So that is like negative 1.0001 or something like that. So that is a number that is just below the asymptote of negative 1. So this is below the asymptote, below the HA. Test a number that is bigger. Okay, 100 should be sufficiently large to see the asymptotic behavior. Again, negatives and positives, as we saw in the last question, come out to the exact same thing. This is an even function. If you divide those, you get something like 1.0001 as a negative, okay, which is also below the horizontal asymptote. So we have horizontal, vertical asymptotes, we have intercepts. The next thing we move to is the part D of this, which is the intervals of increase and decrease. Intervals of increase and decrease. So what we need to look at for that is to consider for the first time in this equation the derivative, which is way back at the top of this slide. So my derivative was 2x over 1 minus x squared squared. My derivative was 2x over 1 minus x squared all squared. Okay, so to figure out the intervals of increase and decrease, you set that equal to 0. You would cross multiply and you'd be left with 2x equals 0. Divide by 2 and you've got the same point that we found before. You have the point x of 0. If you plug that back into the original, we know it hits at 0, 0. So x of 0 is a critical point. It could be a maximum, it could be a minimum. Okay, but critical points aren't just the points that make the derivative 0, they're the part that make the derivative undefined. So plus or minus 1 also need to be considered. So if I set up a number line with -1, 0, and 1 on it, I have some intervals that I want to test. I want to test less than -1. I want to test between -1 and 0. I want to test between 0 and 1, and all numbers bigger than 1. So one way to do this is right on the number line. Another way to do this test is to consider an interval table. So I'll draw the interval table. So on this side of the interval table, I will put what the intervals are. Less than -1, between -1 and 0, between 0 and 1, and the last interval would be greater than 1. Across the top of my interval table, I'm going to put the components of the derivative, meaning a 2x is going to get one column, the denominator of 1 minus x squared squared will be the other column, and then I put a little double line to show that I'm summarizing what the derivative would be equal to afterwards. So I'll continue to put some lines in here. Okay, so thinking of numbers that you would plug in to test, a number less than -1, a number like -2 is a great number to choose. Between -1 and 0, so we'll plug in maybe -0.5. Here we'll plug in 1/2, and here I'll plug in 2. Those are the numbers that I'll plug into my derivative here to see if it's positive or negative. Plugging a -2 into 2x gives a negative. Plugging a -2 into 1 minus x squared squared, well, folks, it's a square, so it's positive. In fact, I'm just going to fill that in, that it's always positive. You're squaring it. What could you possibly put in there as a real number that's going to give a positive? And the answer is nothing. So, if I have a negative multiplied by a positive, that gives me a negative number. That negative number means it's decreasing. If I plug in -0.5 into 2x, I get a negative number and a positive, so it's also decreasing between -1 and 0. Plugging a number like +0.5 in, the first column's positive, and the second, and when you multiply or divide those, you get a positive number, so that means it's increasing there. And plugging in a number like 2, it is also positive in both spots, so it's increasing. So, the only place where it changes from decreasing in this interval and increasing on that interval is at 0. So clearly at 0, you have a minimum going on, because it's going down, then going up. Okay, so here, clearly it goes from decreasing to increasing, therefore you have a minimum. And that minimum point is at 0, 0, as we've established. Alright, so now we have part D was our intervals of increase and decrease, which are reported right there. Part E was max min, which we have now just determined from the table. So part E is easy to accomplish. We now go to the penultimate step, which is step F. I've got a little bit past there, so I'll try and keep that on there. And F wants us to look at the concavity. And for concavity and inflection points, you need to consider the second derivative. Okay, so the second derivative of this function is f double prime, and it was reported as 2 bracket 1 plus 3x squared divided by 1 minus x squared to the 3. So that's my second derivative. Again, same process as the first derivative. You set that equal to 0. So we'll cross multiply, and you have 2 bracket 1 plus 3x squared equals 0. Divide both sides by 2. It still equals 0. Haul the 1 to the other side. You get a negative. That's going to be a problem. You have negative 1/3. You try and take the square root of that, and things break down in a hurry. Okay, we can't plug in negative 1/3 and take a square root. Square root of negatives are undefined. So that means that there are no inflection points. So just because there's no inflection points, though, doesn't mean that we can't test concavity. We can still test concavity left and right of our intercepts. The negative 1 and the positive 1 that we found before, our intercepts, our asymptotes. We have an asymptote at negative 1. We have an asymptote at positive 1. And we're still going to test on intervals in between those asymptotes and on either side of it to see where is it concave up and where is it concave down. So a very similar interval table to what you saw here. Okay, the intervals are slightly different. It's x less than negative 1. It's between negative 1 and positive 1, and greater than positive 1. My intervals are going to be the stuff that's in my derivative, second derivative. So 2 times 1 plus 3x squared is one column. 1 minus x squared cubed is the second column. I put the little double line to symbolize I'm summarizing for the second derivative. Okay, so choosing some numbers here. A number less than negative 1, negative 2 is a great choice. A number in the range, 0 is a great choice between negative 1 and 0. And a number bigger than 1, might as well choose 2. Or pi, whatever you want to choose there. So, plugging in a negative 2 into this first column, you're taking the negative number, you're squaring it, you're multiplying it by 3, and you're adding 1. No matter what you put in, that's a positive. You've squared it to make it positive, you've tripled it, you add to it, and you multiply. I think this whole column's plus no matter what you plug in. Okay, I'll look at the next column, plugging in a number like negative 2 right here. You have that negative 2 you square to get 4. 1 minus 4 is a negative number, and when you cube it, it remains negative. So, a positive and a negative makes a negative when divided. And in this table, it doesn't mean increasing or decreasing. A negative means that it is concave down. It means it's frowning there. The graph is looking down. Okay, so then at 0, plugging in a number 0 here, 1 minus 0 is positive. You cube that, you get a positive. So I get a positive for my second derivative. That means it is concave up. That means it is smiling. And a number like 2, again, would give you a negative number in there. And that means the second derivative is negative, so it is again concave down. So after all this work, you don't have a whole lot of information to put in. Okay? We have on a graph, I'm just doing a sketch so it doesn't have to be an accurate graph. Y and x-axis is defined. Okay, at positive 1, we had a vertical asymptote. At negative 1, I have a vertical asymptote. And at negative 1y, I have a horizontal asymptote. I know that 0, 0 is a point on the graph. It's my only intercept, and it happens to be a minimum. I tested, I found out that I was just below the axis here, the asymptote here. I tested and I found out that on this side the graph goes down to negative infinity. I tested on this side, I found it was going up to positive infinity. This side was going up to positive infinity. This side was going down to negative infinity, and this side was below the axis. So filling in the rest of this information, I don't have inflection points to put in. I know that the table said that the function was decreasing all the time in between these points. So if I drew the graph like that, it would show that it's steadily decreasing. The y values are getting smaller and smaller and smaller as you go left to right. And that also looks like it's concave down. So it's decreasing and it's also concave down. So it's fitting the criteria that I've set. This 0, 0 is supposed to be a minimum. So if I connected these dots, had it come down, hit that minimum, and then climb back up, then I have a graph that shows that it is decreasing up to 0. So it's decreasing here. The whole interval, it is concave up. So that's matching up with what I've drawn. And I show that it's increasing between 0 and 1. The last thing I have is an interval that said from everywhere from 1 beyond, it is continuously climbing up higher, higher, higher. And this continuously climbs because it's approaching that asymptote without ever hitting it. So this entire interval here, it is increasing. It's like a frown, it's opening downward, so it's concave down. Again, all that information in my graph is absolutely consistent with the information I've gotten from the derivatives and my integral tests. So that, my friends, is the graph of this function you could test with technology. You'll see a couple of other examples that have a little bit more to it, but this was a good basic example to get you started.